The second set of transformations that we want to discuss are what we call non-rigid transformations. Previously, we said a rigid transformation was one that didn't change the actual shape of the function, it just changed its position. Well, then it would follow that non-rigid transformations are transformations that actually change the shape. So they actually just change the shape of the function. So this is pretty easy to visualize if we think about our graphs as being made of some type of non-rigid material. So take, for example, this function here that's a quadratic. If we were looking at this quadratic here, you can imagine that this quadratic, imagine it were made out of rubber. And if I could algebraically do something to the function that causes it to change its values, then now this function can either stretch out or get potentially kind of stouter. We can pull on this parabola from either direction, either vertically or horizontally. If I were to pull on this parabola vertically, you would see that it would get skinnier. If I were to kind of compress the graph vertically, then you would see that it would get more compact and widen out. So let's actually break this set of non-rigid transformation down into two separate terms. We've got what we call a stretch or a shrink, and this pressure can be applied from either direction. Let's talk about vertical stretches and shrinks first. We would say that a function stretches vertically when the following is true. When h of x is equal to our function f of x times some constant c. So our original parent function times c, if that c value is greater than 1, then we have what's called a vertical stretch. If that c value is less than 1, but still greater than 0, because all that means is if it's less than 0, now we also have a reflection. But if that c value is less than 1, then now we're looking at a vertical shrink. Let me see if I can pull this up here on my Desmos. Let me pull this up. All right, so take, for example, this original parent function here. Here's our parent function. We've got the quadratic. Hopefully you can see that okay. So we've got our quadratic here. Now, let's look at what happens right now. If, notice the constant here, I labeled it as a here, so don't worry too much about what it's called, but we've got our function and we're multiplying it by a. If that a value is greater than 1, notice what happens here. As a increases past 1, it's kind of like I'm pulling on that function vertically, which causes it to kind of thin out. Imagine you pulling on a rubber band, and so it's thinning out, right? So if I put it back to 1 here, just so I can model that one more time, as I increase that constant that I'm multiplying by, I'm applying a vertical stretch, which causes the function to appear as if it's getting skinnier. Now, if I go back to 1 now look at what happens as I start to decrease to a value less than 1. As I decrease to a value less than 1, that function is starting to widen out. It's almost like I'm pressing down on the graph, or you're smushing down on a sandwich or something like that. And it's widening out. Now, I don't want to go past 0, because if I go past 0, you can probably figure out what's going to happen. It's going to reflect over the x-axis. So as we approach 0, that graph is going to widen out. That's called a vertical shrink or a vertical compression. Okay, so let's go back to our notes now. Now let's talk about horizontal stretches and shrinks. Okay, let's talk about a horizontal stretch. Well, what does a horizontal stretch look like? Well, this time we would say when h of x is some function, and this time, like all horizontal transformations, we're multiplying our argument now by c. We're multiplying our argument by c. H of x is equal to f evaluated at c times x. Okay, now this one's going to be a little different though with horizontal. We were going to say when c is less than 1 but greater than 0, then we have what's called a horizontal. Let me actually write both out first and then you can zoom out here. We're going to have a horizontal stretch. Okay, let me take this away for a second. We have a horizontal stretch. When c is greater than 1, we then have a horizontal shrink. This time the pressure is coming from the horizontal direction. So imagine if you are squeezing on the graph from both sides. If we're squeezing on this parabola from both sides, right? And our c value is greater than 1 and we're squeezing from both sides, it's going to appear skinnier. One easy way to remember this is to remember that when your c value is greater than 1, both graphs are going to get skinnier, if you will. The difference is where that pressure is coming from. When c is greater than 1 with vertical stretches, then we're applying the stretch vertically. When c is greater than 1 horizontally, then it's getting skinnier by me compressing the graph on the sides. And again, if I could just show this graph, hopefully this will work okay. Let me move this to the side. So again, there's my parent function. It's a quadratic. Now let's look at this graph right over here. Okay. This time, notice my constant is we're multiplying our argument by our constant. When this b value increases, pause and think about for a second, what do you think is going to happen as our b value increases? Well, remember, again, the graph is going to get skinnier. And how is it getting skinnier? We're applying the pressure horizontally this time. It's like we're pushing on the graph from both ends. When b is less than 1, but still greater than 0, now we have a horizontal stretch. It's like we're pulling on the ends of the parabola from the horizontal directions. Okay? So when b is between 0 and 1, we have a horizontal stretch. When b is greater than 1, we have a horizontal shrink. Okay? So hopefully that helps see that. Let's take a look at how we would write our transformations. If again our parent function is x squared, what would g of x, if it's equal to 2 times f of x, what would that look like? Well, we've already kind of graphically seen this, so I'm going to skip over the graphs and just write the transformations. We would say a vertical stretch by a factor of 2, okay? And I'm going to abbreviate a bit throughout this lesson, and that's totally fine as long as you are indicating all the key information. What about this g of x here? G of x is equal to 1/2 times f of x. Again, we're multiplying the output of our function by 1/2. So this time we would say a vertical shrink by 1/2. This is a vertical shrink by 1/2. Now I know some teachers might say, oh, you should write vertical shrink by 2 because it's twice as shrunken as it once was. Honestly, I don't mess around with any of that. Just write down the constant that you see in the function, and that's what we can use. Okay, so that just makes life a whole lot easier. All right, you could argue the semantics of whether or not that's fully mathematically correct, but I found that just the easiest approach in communicating what you're trying to say. All right, so now in this last one here, g of x is equal to f times 2 of x, or f evaluated at 2 of x, 2x. This time we're multiplying our argument by 2, so this would be a horizontal shrink, again, by 2. If you wanted to say it's half as shrunken as it once was, that's fine. I would accept that. But horizontal shrink by 2 is sufficient there. Okay. All right. Now let's look at some transformations or some functions that appear to be a number of different transformations. So here, a few things I want to emphasize is that order does indeed matter. Order does matter. With that said, there are multiple ways that you can write these transformations and still arrive at the same transformed function. So just because order matters doesn't mean that there's only one way to write your solution set or the set of all the transformations here. As you'll see, there are a couple different ways we could write this. With that being said, students often ask me, what is your approach or what would you recommend as being the preferred order? And in general, I recommend starting with what is happening to the argument of our function first. Okay, so what is happening to your x first? In other words, I would recommend starting with horizontal first, and from horizontal first, I would recommend starting with following the order of operations. That is to say, do the stretches and shrinks first, and then go with any reflections, although you'll see in a bit that that doesn't matter too much, and then any shifts. So do the horizontal stretches and shrinks first, then reflections if it applies, then any shifts, and then move on to the same order for vertical. So describe what's happening with our arguments first before going into the vertical transformations. And this might make more sense when we actually see some problems. So look at this first example here and ask yourself, is anything happening to my argument? Is anything happening horizontal? Do I have any horizontal transformations? And the answer is no. Nothing is happening to just our argument. Everything appears to be vertical. So we will say first, we are going to have a vertical stretch by 2. Then we have a reflection over the x-axis. Now, pause. Could I have switched the order of these two transformations? And the answer is yes. That totally works. You could have switched the order there and still have had and it would be completely fine. Whether or not you multiply by 2 and then -1 and then or -1 and then 2, that doesn't matter. So that totally works. So now that we've taken care of this -2, now we move on to the -2 down here or to the right. So we're going to say we have a vertical shift or vertical translation down 2 units. Okay, so that one wasn't too bad. Let's try the next one. Let's look at this one here. Well, the first thing I can say is this looks like it's a horizontal shift to the right 2 units. Or is it? Look at this carefully, because I know that your first instinct might be to look at the parentheses and say, oh, it must be horizontal. But ask yourself, are we subtracting 2 from the output of this function, or are we subtracting 2 from the argument? That is to say, is there a difference between what we see here in the parentheses and this? Are these the same? And the answer is no. Here, in what I've written up here, I'm subtracting 2 from the argument. That would make this horizontal. The way it's written here is not a horizontal shift at all. So we would say this is actually a vertical shift, and we're going down. So we're going to say vertical shift down 2 units. And then I would say that this is a vertical stretch. Oh, excuse me, a vertical shrink by 1/2. Now, I know what some of you are thinking. Some of you might be thinking, wait, could I have distributed that 1/2 and written it as such? And the answer is yes, you could have done this. And if you do that, you would get a different set of equally valid transformations. So if you write it this way, what would be the required order? We would say this is a vertical shrink by 1/2, and then we have a vertical shift down 1 unit. And this is an equally valid set of transformations. Notice that within each set, the order does matter. That is to say, it would be incorrect to say we vertically shift down 1 and then shrink it by 1/2. It is this vertical shrink by 1/2 that causes that shift to go from 2 to 1. Because you're shrinking the graph vertically, the amount of shift now is changing. So for this reason, if you're going to go in what I've done here in terms of distributing the 1/2, that's fine. You just got to make sure that you write your transformations in the correct order. But either one of these are valid and would be acceptable. Go ahead and pause the video and try this last one now on your own. Well, if you've had a chance to try it, let's discuss it. What I would recommend is the following, is to look at what's happening to your argument here, because whenever we're doing transformations horizontally, we always want to set our argument equal to 0, because we're trying to undo or find the inverse operations here. So this is equal to -1, and let me just continue this here. X then is equal to -1/3. So what are we saying here? We're saying because of this horizontal shrink, because we're shrinking our function horizontally, that's going to change the shift. That is to say, we could write the following. Horizontal shrink by 3, and then a horizontal shift to the left 1/3 units. Okay, now if you instead wanted to say, well, could I first say horizontal shift to the left 1 and then shrink it by 3? That would work as well. That would result in the same transformed function. Okay, but if you're going to state the horizontal shrink first, then you have to indicate now that your shift, the amount that you're shifting by, has changed because you've already done the shrink. If that makes any sense. All right, now let's move on to this part here. Now we're doing the vertical transformations. So again, pretty similar to what we did in the first problem. We have a vertical stretch by 2, and then a a reflection over the x-axis. And again, you could have flipped this order and been totally fine. And let's go do the final transformation, which is a vertical shift up 4. Okay, and so that would work as well. So again, my recommended order is to do what's happening to the argument first. So take care of the horizontal transformations. taking care of anything following the order of operations first. So multiplication first before we do addition and subtraction. And then take care of what is happening vertically. Again, doing stretches and shrinks first with reflections, and then followed up by vertical shifts at the very end. Okay? So try these practice problems here on this page, and in the next video, I will discuss briefly on how to graph transformed functions.